Hey everyone, this is Derek, and this is section 8.4, Graphing Rational Functions. And I think this will probably end up being a two-part video, has about 6 topics in it. So I'll start with going through a bunch of different features of rational functions, and then once we have all those features, I think there's about 4 things to look at there, then we'll put those together into graphs. And so first, let me start, what's a rational function? They usually use R of x, capital R for rational, I think. And it's just the ratio of 2 polynomials. So some sort of fraction, some division happening in it. For the domain of rationals, the domain is all real numbers except for the things that would make the denominator 0, because remember, division by 0 is undefined. And so what we do to find the domain is we set Q is usually the letter they use to denote the denominator. We set that to 0 and solve. Our parent functions, so we have kind of a couple of flavors. We have basically, our most basic version of this is 1 over x. And so notice 1 over x, that's to an odd power. And so we're getting this graph that I'll show in a little bit more detail here in a second. But that's going to be 1 over x squared, or an even power, which is giving us this other shape. So for 1 over x, if I have y equals 1 over x, and I think about a table for that, x, y, if x is -1, I would get, -1. If x was -2, that would come out a half, -3, 1/3, -10, 1/10. So you can see it's going to get closer and closer to the axis underneath. As I approach 0, if I put in -1/2, 1 divided by -1/2 would make -2. So you can see this is going to start to get closer and closer to the axis, but it's not going to be able to touch it because it's undefined at 0. So I can keep getting closer and closer. If I put a -1/10, so really close, this is all the way down at -10. On the other side, it does the exact same thing, except it's just doing it from the positive. So if I put in 1 over 2, it's a half. 1 over 1 would be 1. 1 over 1/2 makes 2. And so it's going to approach. And so what we're seeing with this graph is we have a couple of end behaviors going on. There's an asymptote. An asymptote is a value that the function approaches as it goes to infinity. Well, at least a horizontal asymptote. So in this case, as we go to negative infinity, we're approaching 0 from below. As we go to positive infinity, we're approaching 0 from above. So that's going to be a horizontal asymptote. We'll see those in this section. Likewise, this has a vertical asymptote, which is what we get when we try to divide something by 0. So here, when I try to go 1 over 0, we keep saying that's undefined. What's happening is we're getting the graph that's firing up to infinity on one side, down to infinity on the other. Because as we divide by things that are closer and closer to 0, if I put in 1/1000th in this, it comes out 1,000, right? So as I get closer and closer to the axis, this is just going to keep getting larger and larger without bound. So that's sort of the asymptotic behavior that we're going to see in this section. We're going to have these horizontals and these verticals. Verticals will come from zeros and denominators. Horizontals I'll talk about more when we get there. We can also have obliques that will go with the horizontals. So for 1 over x squared, it works in a similar fashion to this. The shape is a little bit different because of the squared, but the place where it's really different is because of that squared, we're not going to get negative outputs. When we put in negative values, like say I put in -1, -1 times -1 would be 1, 1 over 1 is 1. So you can see the range on this is going to be positive values. And in terms of the asymptotes, this vertical asymptote right here, notice both sides of the graph are going off together. We're going to see that anytime there's a squared involving the asymptote. And when they're going off opposite directions, we're going to see that one to the first. So let me break this down to a bunch of little steps in this first video. And then in the second video, I'll do, I think, the graphs and then finding equations. Okay, so these first couple of questions are asked to find the domain of the following functions. And remember, we find the domain by setting the denominator equal to 0, because we're looking for the places that we're going to have these asymptotes, or there's also holes coming up as well. But it's where there's division by 0, that's what's going to have to be excluded from the domain. So for this first one, we're going to say 2x plus 7. I'm going to solve it as equals 0, and then I'll rewrite it as the negative at the end. I'm going to subtract my 7 over, so 2x equals -7 divided by 2. So x equals -7 halves. So this is the number that can't be in the domain. And so the way that we would say that, I think on the computer it has the box set up with this, and then maybe x cannot equal, and then I believe they give you a box, and then you're putting the -7/2 in there. But so this is our domain. If I wrote it in interval notation, would be everything except that value. For this next one, so this we're setting, again, the denominator to 0. So x squared minus 4 equals 0. Careful to not do the bring the 4 over and root both sides and get 2, because you lose a root that way. You have to do plus or minus when you do the root, so it might be safer to factor, so I'll show it that way. And so here I'm getting x could not equal plus or minus 2, because those are my two zeros. You might notice up here, let me rewrite this, when I factor, there's this question of these x minus 2's cancel, and so would the domain be, it can't be -2 or 2 or just -2? And the answer to that is domain is always relative to the equation given. So if there's something that reduces out like that, that is going to be something fairly specific, which we actually see on the next page. But that said, it is still, if I put, what would it have been, 2 in this case? If I put 2 into the original equation, 2 squared is 4, 4 minus 4 is 0. So it does not work. So we're always doing relative to what's given in terms of the domain. And then let me show you on the next page how this is different from one another. Okay, so the domain is totally tied to the idea of vertical asymptotes, but there's also what's called removable discontinuities, or probably better labeled as holes. I think on the homework questions it calls them removable discontinuities, but you can think of it, it's a hole in the graph is what that means. So both of these ideas come from the domain. On this last problem, what would happen is the thing that reduces out, that's going to end up being a hole. The thing that stays behind, that's going to end up being a vertical asymptote. And so there's this reducible factor in there, has meaning. It means at that one point, x can't be 2. So it's just basically removing that point from the domain. So it's a removable discontinuity. So first we're asked to find, actually let me go through the definition. So vertical asymptote, if we have this function, if we have this in lowest terms, so we've done our reducing, then whenever makes that denominator 0, that's where your vertical asymptotes are going to be. And then if p and q, these functions up here, share a common factor, that point will be a removable discontinuity or a hole. So that's what I just showed with the example, but there's a little bit more formal version. So for this first one, it is already in lowest terms. Cool. So then that just means I set the denominator equal to 0, and which would just be, right, x minus 6 equals 0, so x equals 6. So this is the number that is not in the domain, and that is the equation of the vertical asymptote. So if this was a graph, I'd have 1, 2, 3, 4, 5, 6. X equals 6, that means I have a vertical asymptote right there. And so that's I'll abbreviate it as a VA. And then this graph would do some version of that. And then this one doesn't have a hole because it's lowest terms, it doesn't share a common factor. This next one, this one would be x minus 5, and then this factors to x plus 5, x minus 5. And so this one does have that reducible factor, which is what this is talking about. And so that's going to produce a hole. So we're going to have a vertical asymptote at this, because when I reduce, I just have x plus 5. So VA at x equals -5. And then at x equals 5, we're going to have a hole. And what we do is we put the 5 back in the original, or we put the 5 in the reduced form of the function, because if I put the 5 in the original, I just get 25 minus 25 and I get it's undefined. But if I put 5 into here, in the reduced form, then I can see where it would be if it were to exist. And so this means I have a hole at when x is 5. If it could be 5, the y would be 1/10. And so in this case, I would have something that with a vertical asymptote at -5 over here. And this would be coming in like this and this. It would look just like this graph, except when x was 5, there'd be a hole right there. And it would keep going. So that's the only difference between this graph and this graph, is that little spot at 5 1/10 is undefined. Okay, so this next box has some really formal notation in it. And I think, you can read the formal stuff. I think I'm going to hop down here and just try to like get to the part where it makes sense. We're going to look at 3 possible things for horizontal asymptotes. And the way that you can determine what's going on with the horizontal asymptote is by comparing the leading coefficients. That's what this is saying. Given a rational function, we're going to compare the degree of each of those leading terms of the numerator and denominator. And there's going to be 3 things that can happen. We can have the numerator is smaller than the denominator, and I'm just going to call that small over big. These could have the same degree. I'm going to call that same because it's easier to remember. And then we're only going to look at cases where it's 1 degree apart, but the numerator could be 1 bigger than the denominator. That gives us our 3rd case. So those are the 3 things that we're going to look at. Let me do a couple of examples just to try to like flesh out what that meant. So if I have something like x plus 2 over x cubed minus 5, that would be an example of small over big. So the degree of the numerator is 1, the degree of the denominator is 3. This would be the same thing as if I had 1 over x. Here the degree of the numerator is 0 and the degree of the denominator is 1. So anytime the degree of the numerator is smaller than the denominator, the horizontal asymptote is going to be y equals 0. And the reason for that is, if you think about the simplest case, 1 over x, as x gets very large, 1 divided by very large is basically 0. And it doesn't matter if this had been x and this had been x squared, because it would reduce. Even if I put a 1 and a 1 on there, now it doesn't reduce. 1,000,000 divided by 1,000,000 squared is still really close to 0. So anytime you have smaller degree on top, larger degree on the bottom, y equals 0. For the next case would be same. So say I have 2x plus 3 over 5x minus 1. So again, if we think of x as 1,000,000, because that's what these asymptotes are talking about, the horizontal ones are what happens as we go out to infinity. If x was 1,000,000, this would be 2,000,003 divided by 5,000,000 minus 1, which is pretty much 2,000,000 divided by 5,000,000, which is pretty much 2/5. And so all you're doing is using the ratio of the leading terms. So that's what this says. If the degrees are the same, it'll be the ratio of the leading coefficients. And then the last one is where we have big over small. So that would look something like x squared plus x plus 1 divided by x plus 2, for instance. So here, the degree of the numerator is 1 larger than the degree of the denominator. And what we're going to have to do there is that long division or synthetic division if it's available. And we're going to get something that will be a linear equation. And instead of having a horizontal asymptote, we're going to end up with an oblique or slant, depending on which book you're using, asymptote. And so, that is, so small over big, y equals 0, same, ratio of leading coefficients, big over small, long divide to get oblique. So once, this is sort of, again, the formal version, but this is sort of what I keep in my memory just to be able to do the problems. Okay, so for this question, we're asked to find the domain vertical asymptotes, horizontal asymptotes of the function, and list all domain restrictions and asymptotes in order from least to greatest. So that part right there is just for the computer, so that's how they've programmed the question, is to go small to large. So this first function we're looking at, we got x minus 2 over x plus 2, x minus 2. And we're asked to find the domain. So this, careful, because we can reduce, but when we're doing domain, it's always relative to that original function. So I'll say x cannot equal -2 or 2 is how the computer's going to want that, because of the least to greatest. We're asked to find the vertical asymptotes. So the vertical asymptotes do come from the denominator, but remember this is when where it reduces. So that would be a whole. So my only vertical asymptote in this case is going to come from that factor, which would be a -2. And then domain, vertical, and horizontals. So this is the degree of the numerator is 1, degree of the denominator is 2, so it's small over large. And so that is going to be y equals 0. And just a note on vertical asymptotes, these are going to be absolute when we're graphing. You cannot cross a vertical asymptote. Horizontal asymptotes, they can be crossed in the middle of the graph or in the interior part. They describe the end behavior, so they're describing what happens as we go out to infinity. But in the middle of the graph, they can absolutely be crossed. This next one, so we got domain, so we got to get this factored. So let's get an x out of there. That's going to leave us x squared minus 6x minus 7. And then x looks like plus 1 and x minus 7. And so my domain is going to be all real numbers except x cannot equal, in order would be -1, 0, and 7. And in this case, the vertical asymptotes are going to be that exact same thing, because notice up top, if I factor that, I could take out a 2, but that's 2x minus 1. There's nothing reducing. So my verticals are going to be x equals -1, 0, and 7. So as long as there's not a hole, the domain and the vertical asymptotes match. But in this case, that one was a hole. And then horizontal degree here is 1, degree there is 3, so another y equals 0. Okay, same directions. So domain on this one is going to be x cannot equal 4. Range on this one will be x equals 4. I'm sorry, not range, vertical asymptote. And then this time, this is x to the first over x to the first, and these have invisible ones. So our horizontal asymptote is going to be y equals 1 over 1, which would be y equals 1. And so sometimes you'll get, it's the too easy, it's hard, but just remember if there's nothing there, that is an invisible one. This one right here, first let's get this rewritten so it's in descending order. So we got -3x plus 2 over 7x plus 1. So now my domain will be that 7x plus 1 doesn't get to make 0, so we'll bring the 1 over. 7x equals -1, and then dividing, x can't equal -1/7 for the domain, which makes that the horizontal asymptote again, because no reduction. And then, I think I just said horizontal, I meant vertical, sorry. And then the horizontal asymptote, once I wrote that in descending order, hopefully now it's clear that there's the ratio of my leading terms, because those are same over same. And so this would be y equals -3/7. Okay, these next two examples are slant asymptotes, or oblique. You'll see different books will use one of those two terms generally. And so this is where we have the degree of the numerator is 1 larger than the degree of the denominator. It could be more than 1. We're just going to look at ones that are linear, but you can have quadratic asymptotes and cubic asymptotes and as many degrees as there are. But we'll just stick to linear ones. So in this case, this is where I have to do the long division and then find the equation of the line that's left. So we're going to go 3x plus 2 into 9x squared. And so even though there aren't terms here, I'm going to need them in a second. And that's the thing where I have to have placeholder terms. Because the first thing I got to do is go, what do I multiply 3x by to make it 9x squared? Because I'm going to 3x goes into that. Well, they go 3x times, so I need somewhere to write that. So now I have my 3x times 3x, 9x squared. And 3x times 2 gives me plus 6x. So I'm picking up a linear term whether I'm starting with 1 or not. So that, again, is why we need that placeholder. 0 minus 6, -6x, bring down the 0. And then what do I multiply 3x by to make it -6x would be a -2. -2 times 3 is -6x. -2 times times +2 make a -4. And then negative minus a negative be negative plus and so that makes 0. 0 minus -4 make that a 4. So my answer to this long division problem would be 3x minus 2 plus 4 over 3x plus 2. But for large values of x, 4 divided by 1,000,000 is basically 0, so this piece drops out. So that's why the asymptote ends up, what it's going to approach, since this goes to 0, is this line, 3x minus 2. And then this next one is a bit more straightforward in terms of the long division. And actually, I think on this one I will do synthetic because it's available, so let me use this as a reminder on how to do that. So for synthetic, we go 1. We use the 0 instead of the factor, so what makes x minus 1 0 would be 1. And we grab our coefficients from this one. And then we bring down the 1. 1 times 1 makes 1. -6 plus 1 would be -5. And then 1 times -5 makes -5. And that's our remainder. We don't care about the remainder. That's the only part we care about. So x minus 5. So y equals x minus 5. And you can do that one this way as well. And you'll get the exact same result. Okay, so then here's the last topic for sort of all the pieces. And then I'll cut this video. And then in the next one, we'll put all of it together. So this is asking for now x and y intercepts is what we're trying to work out. So to find a y-intercept, we just let x equal 0, right? And that's what it's always been. To find the x-intercept, we let y equal 0. So let me show you what that would look like here. So if I am finding the x-intercept, I'm going to let y equal 0. So that means I'm going to have 0 equals x minus 5 over x squared plus 2. So if I go to solve this, watch what happens. I multiply both sides by the denominator. And where I end up is these canceling, and I have 0 times this, so it knocks that out. And 0 equals the numerator. And so to find an x-intercept, all I have to do is set this numerator equal to 0, and that's going to be where my x-intercepts are. So from the denominator, when we set that to 0, that gave us domain. Numerator to 0 gives us x-intercepts. And then bringing that over, we get x equals 5. So we certainly don't need to do all those steps. Now we'll just look at it and go, x is 5. But that's the how come I can do what I'm about to do on that next one. So x, writing that as an ordered pair is probably the better plan. So when x is 5, y is 0. And then to find the y-intercept, y equals 0 minus 5 over 0 squared plus 2. So notice the zeros knock out everything that had an x, and then what's left, this stuff on the end essentially, is going to be your y-intercept. The same as it is with a line. If we have y equals mx plus b, once x is 0, that's why that's your y-intercept. So we're seeing that here as well. So in this case, the y-intercept would be when x was 0, the output was -5/2. So I'll do this next one a little bit shorter, since now we have hopefully that. So to find my x-intercepts, I'm going to do x squared minus 3x plus 2, or my numerator to 0. Factoring, I get -1 and -2 equals 0. I guess I should check and make sure this is in lowest terms, because otherwise that would be a whole. And so if I did factor that denominator just to check that out, it'd be x plus 1, x plus 4, and this is x minus 1, x minus 2. So there's no canceling happening, so I do have to note that. So here my x-intercepts are going to be at 1 and at 2. And then for my y-intercept, I'll just let all my x's be 0 with my index finger, and then what's left is plus 2 over plus 4, which is 1/2. So when x is 0, which is covering them all up with my finger, then the y is 1/2.